We're continuing on in Chapter 10 with the subject of biasing. For a transistor to function, the two p-n junctions must be properly biased. The base emitter junction behaves like any other p-n junction when viewed alone. If the base emitter junction is forward biased, the transistor is on. If it is reverse biased, the transistor is off. And so this is just like a diode. If you forward bias a diode, the diode conducts. If you reverse bias diode, the diode cuts off. Now, the base emitter junction in a transistor is going to essentially turn the transistor on or off. Now, the base collector junction will not have that same power, but the base emitter junction will determine whether the transistor is turned on or off. Now, the base collector junction also behaves as a p-n junction, but it will not have the ability to cause it to turn on or off. Now, when we're looking at these two scenarios here, the emitter has been taken out of the circuit and there's no current, and the emitter is essentially open. What we've done here is we've connected a battery across the collector base junction. And in this case, the collector base junction is forward biased, and we are experiencing current flow, and this is much like a diode. And in this scenario here, the same thing, it's reverse biased. The only difference is the polarity of the diode is opposite, and now there is no current. You see the little meters here indicating no current. Here they indicated that the current was flowing. And keep in mind, in both cases, the emitter is open, it is out of the circuit. We're just showing the fact that this behaves just like a diode, and the base emitter would function just like a diode as well. Okay, we're going to be looking at a number of different types of biasing. The effects of simultaneously biasing both of the junctions in a transistor are important to understand. There are 4 possible combinations to bias the two junctions, but only 3 play key roles, so we'll be looking at 3 of them. Okay, the first one is reverse bias BE, base emitter, and reverse bias collector base junction. So here we have a voltage applied to both junctions that will cause them to turn off. Now, if both junctions are turned off, we are in a condition we call cutoff. This is essential for digital. It is not used in linear operations like amplifiers. For digital, transistor only operates as a switch that is either off or on. And the off condition is cut off. The on situation, or the on condition, is going to be called saturation. Linear operation, the entire spectrum between on and off is used. Now, with linear operation, what we'll see is that the transistor never is saturated, and it is never cut off. It operates in what we'll call an in-between zone. But what we're looking at here is cutoff, and what you'll notice here is we have the 2 batteries in the circuit, and they are configured so that both junctions are reverse biased, and so the transistor is cut off. Now, what I might add here is that, remember, we said the base emitter junction essentially controls whether the transistor is on or off. And here we have a negative voltage between this junction. In many cases, what we'll find is it won't necessarily be a negative voltage. It'll simply be a very low voltage. For example, if we had 0 volts here, then that would not be sufficient to turn on this junction. Or if it was less than 0.7 volts, it would not turn on this junction. That would be essentially the same thing as reverse bias, as having insufficient bias. And in either of those cases, it will turn off the transistor. Okay, biasing arrangement number 2. This is forward biasing the base emitter junction and reverse biasing the collector base junction. This allows for maximum current flow between the emitter and the collector. And what we'll find is that it is almost the same current that is going through the emitter will be in the collector as well. We'll pick that up on the next screen. In this case, the base current is very small, so the current that will have a large flow of current through the transistor, but only a very small amount will actually go out of the base connection here. The emitter to base current is heavy. Okay, so current going from the emitter to the base is very heavy. The emitter is heavily doped with free electrons, so we have lots of free electrons here. The base is very lightly doped with just a few holes. If electrons recombine with holes, they can exit through the base. So what we're saying, when we apply a forward biasing voltage to this junction, these electrons will be flooding into the base. However, there's only a few holes in the base, and so for electrons to flow through the base, they need to do it as a function of holes. So what will happen is that a few of these electrons will find their way into holes and then find their way out the base. But what will happen is that most electrons will see the positive on the collector. Okay, there's a positive up here, and they will enter into this depletion layer. Remember, this is the area depleted of carriers, but remember also that we have this layer is extremely thin. In this picture here, I've shown it quite large, but actually it is extremely thin, and this mass of electrons flows into the base. There are insufficient carriers to move those electrons out through the base connection, so most of them will be swept into the collector and come over here to the positive side of the power supply. And so what we'll find is that most electrons are going to go all the way through to the collector, and only a small number of them will actually go out the base. And we're going to continue this on the next page. The transistor is constructed to encourage current flow from the emitter to the collector with this type of biasing arrangement. The base is lightly doped, which makes recombination difficult. As remember, I mentioned there's just a few holes here, and in order for those electrons to flow out the base, they must recombine with holes and then go out the base. The base is very thin, which makes it more probable the free electrons will encounter the base collector depletion layer before they find a hole. So most of these electrons that flow into the base are going to move into that depletion area and actually flow into the collector and over to here. Now this seems to kind of contradict what we have talked about before, that when you have a reverse bias, you don't have much current flow. And in this case, we have a reverse bias condition here, but there's a couple things that have contributed to that. The fact that the base is actually very thin, and the fact that there are very few holes, so that the method for current to flow through the holes is going to be limited. So most of the electrons here will move into the collector and over to the positive plate of the power supply. Now, 95 to 90% of the electrons will flow through the collector. So we're saying the vast majority, in fact more than the vast majority, virtually all of the electrons will flow from the emitter into the collector. And we're saying 95 to 99% will do this. In fact, in many circles, when you're talking about the collector current and emitter current, they will simply say that IE equals IC, because so much of that current goes up to the collector. Now there is a tiny amount that goes out here, and there is a term that addresses it. It's called the alpha of the transistor, and the alpha is IC divided by IE. And usually this relationship is going to represent oftentimes you're looking at 99%. So virtually all of the current from the emitter will flow into the collector. Okay, continuing on with this discussion, this configuration is a requirement for transistors operating in, notice, in the linear region. Output will be a wave shape which will be identical to the input. Now that is the characteristic of a linear operation. Now when you have cutoff and saturation, you either have a low or you have a high. There's only two conditions in when you have saturation and cutoff, and this would support digital circuits. But for linear operation, the output will be identical to the input. And I'm going to jump ahead just for a moment, then we'll come back. This is a picture of a circuit from your textbook. It is actually figure 10-38, and this is a circuit where a transistor circuit that is set up for linear operation. And I'm going to bring your attention to the waveform here, and you'll notice the oscilloscope is connected to here. The red lead is coming down here, and you see this red signal here is the input, and then the blue one over here is the final output, and that is this signal right here. You will notice that there is phase inversion, but the relative shape of the input and the output is the same, and that is what we're going to see in linear operation, is that the input and the output are the same shape. Now what we haven't addressed here is that actually the output is 147 times larger than the input due to the fact that we have amplification occurring here. But point being that the input and the output are the same shape. Okay, the emitter and collector currents will be almost equal. We have already mentioned that. The base currents will be very small. We mentioned that. If the base current is varied, the emitter and collector will vary proportionally. And this is the basis for amplification. If we look again over at this circuit here, here is the base of the transistor, and here is a signal coming in. That signal would be applied to the base, and the currents in the transistor are going to fluctuate based on that input signal, and that will result in this phenomenon we call amplification. The ratio between the base and the collector currents is small. It is often referred to as beta. Remember, we had the alpha, which was the relationship of the emitter to the collector. The beta is the relationship of the current in the base to the current in the emitter. And we write this as IC over IB. And so this is the relation, excuse me, not between the emitter and base. This is the relationship between the collector current and the base current, okay, IC over IB. And this ratio varies widely. In fact, this is one of the reasons transistors without some additional biasing assistance are in some respects, they're a little bit unstable because this value B is subject to so much change. There's a transistor out there called a 3904, very popular transistor, and this ratio is from 100 to 300. And so from 100 to 300 times larger the collector current is than the base current. On data sheets, this item is often referred to as HFE, and it is a relationship of collector current to base current, and the collector current is usually in the vicinity, in this case of the 3904, 100 to 300 times larger than the base current. And again, this is referred to as the beta of a transistor. And again, here we have our schematic of an amplifier, and in this case we're using the 2N2222A transistor. Okay, in this section we looked at the biasing we looked at the biasing for linear operation, which means that we forward bias the base emitter junction and reverse bias the collector base junction. We also looked at cutoff. In the next section we're going to be looking at saturation, and we will conclude biasing.